The OVIO charging cradle is back on the bench. This time to get proper protection from it possibly killing a PS5 controller. But does it even need protection? Time to do a quick test and find out. First, I'm going to get a baseline reading of the output voltage. 5.31 volts at 200 milliamps. 5.29 volts at 600 milliamps. Pretty good regulation. These resistors, R3 and R2, set the output voltage of the boost regulator. So I'm going to tack a 20k ohm resistor in parallel with R2. That should get me to a damaging level of output voltage, if the boost regulator is capable of it. Okay, 9.3 volts with minimal load. That would probably fry something. 9.28 volts at 200 milliamps. 9.26 volts at 600 milliamps. I think that would do some damage there. I really doubt the DualSense controllers have overvoltage protection. I think Sony would rely on the USB voltage controller. When I drew this diagram up and didn't see any overvoltage protection, I was concerned that a failure in R2 or R3, more likely R3, could destroy a controller. After testing, I think that is a valid concern, and a proper fix is in order. So that brings me to this IC. Notice there are no leads on this chip. So many ICs, especially in the power control area, only come in the no lead packages. This is what I'm going to use to implement the overvoltage protection. I'm using the TCKE805NL for this project. The main reason for choosing this chip, it was in stock and would handle over 10 volts at the input. Can see here that the overvoltage clamp will be somewhere between 5.62 volts and 6.45 volts, so that should be perfect. After all, this chip is made to protect a 5 volt voltage rail. It needs very few external parts to operate. A couple of small filter caps on the input and output. The current limit is set by R1. I'm setting it to over 2 amps, so it should never trip because of overcurrent. The USB supply should shut down first. The inrush current capacitor is set to what the datasheet listed as typical, 1000 picofarad. I didn't see anything about leaving the pin open, so I'm not going to. I'll put the schematic and board layout up on GitHub for anyone who wants to make their own. It just extends onto the end of the boost regulator PC board and shouldn't cause any mounting problems. I'll just push the wires that connect to it up under the board. Alright, let's throw some overvoltage at it and see how it does. 9.3 volts input, 6.35 output, at almost no load. A little less than 15 milliamps. Less than 1/10 of a watt dissipated. It won't thermal trip at this power. It will just act like a voltage regulator. At a 200 milliamp load, input 9.28 volts, output drops to 6.16 volts. A little over 600 milliwatts of dissipation. Once it's closed up in the case, it probably will trip after a bit of time. It's on a very small PC board, which is not much of a heatsink. Now at 600 milliamps, input voltage is 9.27, output is 5.99, so almost 2 watts of power dissipation. Let's see how long before the thermal trip shuts it down. Can't imagine it taking very long. There we go. A lot longer than I expected for that much power dissipation. Now this is the latching version, so we'll have to power it down to get it to restart. The auto retry version was out of stock. I don't think it matters. If it does trip on overvoltage, something has gone bad in the boost regulator, so it really doesn't need to try and restart on its own. It's going to need to be repaired. Now at a normal operating voltage and at a 1.5 amp load, only about a 40 millivolt drop. Can't ask for much more than that, other than maybe a package that has leads on it. I'm happy with that. The controllers can now stay on the charging cradle without any concern about their well-being. And even though there is only a slight chance of either the resistors or boost regulator failing, there is now an extra line of protection. While this is more expensive and complicated than just Zener diodes, this modification gives a much more accurate voltage clamp. And if there is an overvoltage failure, there won't be any smoke. Thank you for watching.